So we will start with the fourth lecture in the special theory of relativity. And as we have already derived the Galilei, or which we also call the Galilean transformations, in this transformation, you remember that we used prime for the moving system and unprime for the stationary system. X prime was equal to x minus vt, y prime was equal to y, z prime was equal to z, and t prime equals t. This was the Galilean transformation, and we were having the Lorenz transformation is the Lorenz transformations, and this was the introduction of gamma. Means it was the same thing here, but only one factor gamma is there, x minus vt, while the perpendicular components to this dimension, y prime equals y and z prime equal z. The only difference here was in the time here, and that was the t prime. T was relative in the Lorenz transformation, absolute in the Galilean transformation, gamma times t minus v over c square x. These are the transformations where gamma is equal to 1 over 1 minus v square over c squared. Now gamma factor, it is called as the Lorenz factor. And if I look over here, when v is very, very less compared to c, then v over c will almost go to 0. And 1 minus 0, it will be 1, and gamma will be equal to 1. And when it is equal to 1, then on the space dimensions, because we are taking dimension, the motion in one dimension, so this is only along x-axis, while the perpendicular dimensions of space y and z are the same. They are not affected. When gamma will be equal to 1, then the Galilean space transformation and the Lorenz space transformation are both equal to, means both are the same, x minus vt and x minus vt. The only difference between them is that when the speed of the body or the frame reaches close to the speed of light, then the Galilean transformation is no more valid, and we will have to go to the Lorenz transformation. The two more components of space, they are the same in both the transformation, while the time, if I look here, the time is absolute here. Whether a frame is stationary or a frame is moving, the time is the same for both of them. But in the Lorenz transformation, time is not the same. Now, even if gamma is equal to 1, like when v is very, very less than c, then gamma will be equal to 1. But even if I put gamma equal to 1 here, then t prime is not equal to t. And due to this, we are having a difference for all the speeds. Means here, time is not the same for all the speed, while over there, space is the same for speed which are much less than the speed of light. Okay. So we can say one thing, that if the gamma will come out to be more than, means its value can be 1 or more than 1, its value cannot be less than 1, because for less than 1 this number should be greater than this one and it will become imaginary, so for that it is not valid. So the gamma value will come out to be equal or greater than 1. If I look here to these one, means this is the direction of motion. So changes are occurring along the direction of motion, not perpendicular to the direction of motion in space. While in time, it is means having no unidirectional, means no components here. So time is different in both the frames. Moving frame time is different than the frame at rest. Now here we will have to take much care about the notations here, that prime notations are for the moving frames, while unprimed are for the rest frame, the frame which we are considering stationary or at rest. When I look to them, like I do calculation with x prime, y prime, z prime or t prime, it means I'm doing these calculations in the moving frame. When I talk of x, y, z and t, then it means I'm doing calculation in the rest frame, in the frame which is stationary. So if we want, the interconversion is also possible, and I can write the Lorentz transformation equations like they are interchangeable, and I can write that x is equal to gamma x prime plus v t prime, y equals y prime, z equals z prime, and t equals t gamma times t prime plus v over c square x prime. Now they are interconvertible. Look here, prime on this side, unprimed on this side. Here I have written the unprimed on this side and the prime on this side. So if it will be position, it will be x prime. If it will be time, then it will be t prime in all of them. In order to memorize them, there is a simple way. Just this is easy to write this one, and then just change these x and t to prime and the minus with a plus symbol, and you will do the interconversion. So if you are looking from the frame of the stationary frame, then you will have to use this one. If you are looking from, means the observer is in the stationary frame, then these are the equations. The observer is in the moving frame, then these are the set of equations. Now there are some predictions of the special theory of relativity, means Lorenz did this thing. Then where was the problem that he didn't resolve? It was, means which Einstein did, and it was that issue of the reference, that if this is light, then with respect to what it is moving. That was the issue which Einstein resolved. We have discussed already this thing in the previous lectures. So some predictions were there. Those predictions are the consequences of the special theory of relativity. They were the very first one which got experimental confirmation, which got most of the attention. It was time dilation. Out of the many predictions that this theory did, special theory of relativity, Time dilation was the one experimentally proved, the one which got more attention and which was the focus of the theory. Then it was having a consequence of length contraction. It's a consequence of this because space and time are related to each other. So the consequence of time dilation was length contraction, but unfortunately, we haven't confirmed this thing experimentally. There are means it is almost impossible to have something of measurable size and move it with a speed closer to the speed of light and then observe the difference. The time dilation confirmation, it was done with the help of the elementary particles. The lifetime of elementary particles, rest lifetime was different than the moving lifetime. And they'd confirm the theory and the time dilation, but no confirmation for the length contraction, but it's a consequence of this thing. So this thing is also possible. Similarly, one of the consequence of time dilation, which was not the right thing to apply here, was the twin paradox. It wasn't a paradox, it was actually the wrong application of time dilation on a phenomenon. So it was not a paradox even, but it became famous with the name twin paradox. And then of the length contraction, some weird type of, you can say, example, the barn and ladder paradox. Barn and ladder paradox. It's a consequence of this one then. But we will discuss them briefly, that how these things are the wrong applications. Another thing was causality. And the last which we will discuss today is simultaneity. So these are the consequences of the special theory of relativity, and we will discuss them one by one. For all of these, we are following the very basics discussed in the D.J. Griffith's book, and that is the main reference with us. So let's first start with the time dilation. So let's consider that we are having, let's say, we are having a box or a car or any other van type, and this is, let's say, moving with velocity v, and we are having a lamp here. Okay, we are having a lamp here which is, let's say it's a laser, so not random light, but it's a laser, and light comes in here to the bottom. Here is a mirror, and from that mirror it bounces back and goes to the top here. Let's say this laser is just fitted here. This light comes in and then goes back. And an observer who is here in this frame is measuring this time. How much time did it take to reach from here, means do the round trip? And another observer is here who is stationary and on the ground. So for this stationary observer, this frame is moving. Now if you ask from this observer that how much time the light took in moving from this point back to this point, so he will very easily say that the time is the distance which the light takes divided by its velocity. Because how much is the velocity? He will simply apply S is equal to Vt, and V is equal to C here because it is light, and T is T prime because the moving observer is measuring it, and it is equal to, let's say we simplify the situation, and we simplify the situation like this, that the light comes in from here and just hit the bottom here. And how much time does it take? Let's say the total distance here is h, and he will say that t prime is equal to h over c. Now if you ask this observer who is measuring time is t, now what this observer will say? According to this observer, this is moving. So the light is not following this path, but according to him, the light just follows this path, right? And it hits here because during that instant, it is now a speed which is comparable to the speed of light. It is not ordinary speed. So this would have moved some distance. How much means this is h, then how much this distance? It will be the square of this plus the square of this distance, and this distance is equal to v times t. Now you will note a difference between the Griffiths notation and our notation, and that is that Griffiths is using delta t, and delta t will be any time minus any initial time. If I consider the initial time is 0, then I will write the delta t is just t. Similarly, for the position, it will be delta x equals x minus x naught. If x naught is 0, then delta x will be equal to x, and similarly the things are true for the primes as well. So now how much time this one will measure, this how much it will say that how much distance the light has, how much time the light has taken while reaching from that point to this point, and he will say that this time is actually t squared is equal t squared like h square plus vt squared, and this distance is c times t. So it will be equal to c square t square. The same Pythagoras theorem we are applying, and Pythagoras theorem is saying that this distance square is equal to this square plus this square. Now this is ct distance, so it will become c square t square, then h square plus vt square. And I can write from here that t is equal to h square plus vt square square root divided by c. Now you may ask that when you divided by c, then took the square root of it, and the square root of it is this by this, but it should have plus and minus here. So plus and minus are here actually, but we don't have any concept of a negative time. and that's why we are only considering the positive value of this one.